So we're on page 535 of the Math 20 Absolute Value Workbook, and we're looking at solving quadratic inequalities in one variable by case analysis. So first off, solving quadratic inequalities in one variable, we can actually solve it in 4 different methods. And so let's just make mention of that first. So in one variable, so there's 4 ways. First way that we're going to look at below is through graphing, and graphing of course is a quick and easy way, particularly if you know how to graph that quadratic and draw that out. It makes it super easy to do. However, if you need an algebraic method, graphing is not going to do. It will help you to check your work, but that's about it. So our other methods are going to be case analysis, which we're going to look at today, and then in lesson 7 it goes through 2 other methods. One is through a test interval or test cases, and the 4th method is through sign analysis. So we'll take a look at those 2 later. Today our focus is going to be on graphing and case analysis to solve our quadratic inequalities in one variable. So what does it look like? So there's our quadratic in general form, ax squared plus bx plus c, and that quadratic is either less than 0, greater than 0, less than or equal to 0, or greater than or equal to 0. And so you can see an example right here, x squared plus 2x minus 8 greater than 0. There is just one single variable. So that's how we recognize that we're dealing with a quadratic inequality in one variable. So the thing to recognize though is one variable versus 2 variable. So if we're solving an inequality in 2 variables, well, first off, you're going to see the 2 variables, x and y, but your solution is a region. So it's essentially a shaded region that represents multiple possible coordinates, ordered pairs that satisfy that inequality, and your quadratic or your line will divide your coordinate plane into 2 regions, one of which of course is your solution region. When we're talking about an inequality in one variable, the solution is actually on a number line. So in this particular case, it's along our x-axis. So what are we looking at then is essentially we're saying, so here's the graph. They've graphed y equals x squared plus 2x minus 8. They've graphed that quadratic equation, that quadratic function for us. So there they've indicated we've graphed that function, and the graph of the function whose equation is y equals x squared plus 2x minus 8 is shown. The x-intercepts are -4 right here, so that's -4, and this is 2. And that of course is when y equals 0. So what we're looking at though specifically for the inequality is what are the x values that when substituted into our quadratic will give us a value for y that is greater than 0. So if you think about it, if I was to, let's say, put in x equals 0, then we're going to end up with the value -8, which is obviously not greater than 0, which is not part of our solution set. So we could go through and literally test a whole bunch of values going through this, but it's actually very, very simple when you look at the graph. It's essentially saying, hey, along this number line, we've got 3 test intervals, we can say, or 3 intervals. We've got the interval which is from -4 and to the left of -4. So for x less than -4, we've got the interval that is between x is greater than -4 and less than 2, and that's right in here. And then we've got this upper third interval right here that is x is greater than 2. And so essentially our quadratic, if it has two x-intercepts or two roots for the equation, it splits our x-axis then into 3 intervals. And so what we're looking for is what interval or intervals provide us values where our graph is greater than 0. And so you can see right here, this arm is y values greater than 0, and this arm is y values greater than 0. And when do we get those? Well, in these two intervals, when x is less than -4 and when x is greater than 2. And so what we can say then is complete the following using the above graph. The solution to the inequality x squared plus 2x minus 8 greater than 0. So when is the graph above that x-axis? Is when x is less than -4 or when x is greater than 2. So along those same lines then, so the x-coordinates of the points on the part of the graph which is below the x-axis, meaning y less than equal to less than 0, is everything in that middle interval, meaning that the solution to that inequality is when -4 is less than x, or x greater than -4, and less than 2. And so how do you know when you use the greater than or equal to sign, or less than or equal to, is basically, are those included in the original inequalities? And so since they're not, then the x-intercepts are actually not part of either solution, because we don't want it to equal 0. It's either greater than 0 or less than 0. Okay, and so the solution can be represented in as an inequality. We can also represent them on a number line. So here we have x less than -4, so open circle, indicating that it's up to but not including -4, and to the left, and the other boundary point not including 2 is on there, and everything to the right. Whereas the solution in B, when is the quadratic less than 0, is that middle interval between -4 and 2. Okay, so it says then for this next question, use the graph of the function f of x is equal to 12 plus 4x minus x squared to solve that particular inequality. So once again, that means we need to know how to graph that. So graphing could be a number of things. So first off, we could actually go ahead and factor that function. That would be helpful. What else would be helpful? Would be, well, we know that when x is 0, if we substitute that in, then y is equal to 12. So that then gives us our y-intercept right here, which is 12. When we go ahead and factor that, then we know that we've got 6 and x and 2 and x, and that will be positive 6 and negative 2x there. So that means that our x-intercepts are then going to be negative 2 and positive 6 then. So our graph is going to look something like this. Then through here, where that is negative 2 and that is 6. So now using the inequality 12 plus 4x minus x squared greater than or equal to 0. So simply it's asking, when is the quadratic, for what x values is the quadratic greater than or equal to 0? So that is, here's a section that is greater than or equal to 0 over the x-axis. So what are the values that give us that? is everything in that middle interval. So on a number line then, so if you were just to draw out that x-axis, then we have everything from -2 to +6, and because it's greater than or equal to includes those, so it's two closed circles, and it's all of those values in between. And so that is what our solution would look like on a number line. If we're stating the solution, then we would indicate that x is everything that is greater than or equal to -2 and less than or equal to 6 then. Okay. So let's take a look. Investigating it then using case analysis in this case. Okay, so when we take a look, they've used Colin, for example, wondering if how he would go about solving the inequality that we previously did in class example number 1 without actually drawing a graph. And so he goes ahead and he recognizes that he needs to factor it because that's going to help give us the intervals. And so what Colin recognizes is, hey, well, you know what, if something times something has to be greater than 0, well then that would mean that both of these maybe perhaps are positive, because a positive times a positive is going to give us a positive that is therefore greater than 0. So Colin sets up the fact that x plus 4 must be greater than 0, and x minus 2 must also be greater than 0. And solving that, then subtracting 4 on each side and adding 2 on each side, so x is greater than -4 and x is greater than 2. So since x, we're talking about the same value here, has to be both greater than and -4 and greater than 2, then it makes sense that the solution itself is going to be x greater than 2. So that means that Colin looks at both of these and says, hey, in order to have them both positive, I can either choose values greater than -4 or greater than 2. And it's got to work for both. So the one that is, like, let's say if I take x greater than -4 and somebody says, oh hey, well 0 is greater than -4, but if I put in 0 into the second factor, 0 minus 2 is not going to give me a positive value. So whereas if I pick any value that's greater than 2, it will automatically also be greater than -4. And so that is why the solution is simply just x greater than 2. So one thing you guys have heard me say once before is that you're picking the one essentially that is more restrictive. If you wanted to graph it even, you could think of this being, okay, I'm looking at all of the values greater than 2 and then all of the values that are greater than -4. So the only values that satisfy both scenarios are those values greater than 2. Okay, and so you can see he checks his solution, and of course we already know that he's only got part of the solution. So at the end of the day, well, you guys probably said something or were thinking something when we said, hey, well, if something times something has to be greater than 0, it's either positive times positive equals or is greater than 0, or else, what else times something could also give you a product greater than 0 is, of course, if we have the other case is that both we could have negative multiplied by a negative. That is going to be then a positive value, so greater than 0. So that complete solution then is also the fact that x plus 4 could be less than 0 and x minus 2 could also be less than 0. So that's the other possibility. And so isolating x again, x less than -4 and x less than 2. And the one that is going to be more restrictive than of the two is x less than -4. And thus our complete solution is going to be x less than negative 4 or x greater than 2. Okay, so let's take a look then. So here's one to start with. So solve the inequality x squared minus x minus 20 less than or equal to 0 by an algebraic process similar to the investigation. So essentially using a case analysis then. So taking a look then, first thing we want to do is we want to know what our factors are. So we're going to factor x squared minus x minus 20, and we know that that factors to x plus 4 times x minus 5, and that must be less than or equal to 0. So our possibilities are either that we have the fact that x plus 4 is our positive, and that is greater than or equal to 0. And if that one is positive, then x minus 5 must be less than or equal to 0. Or the other possibility is that we have x plus 4, which is negative, so that's less than or equal to 0, and that x minus 5 is greater than or equal to 0. So essentially you've got these two pairs that make up our two scenarios right here. So when we solve them, then we've got x is greater than or equal to negative 4 and x less than or equal to 5. And can you think of a single value that is both greater than or equal to negative 4 and less than 5? Yeah, absolutely. So it's actually that whole sets up a range for us. So anything that is between negative 4 less than or equal to 5. If we go to the other side and solve, we've got x is less than or equal to negative 4 and x is greater than or equal to 5. Well, now think again. Can you think of a single value that x could be that is not only less than or equal to negative 4, but also greater than or equal to 5? No, there's no value that exists, so there's no solution in this particular case. So our solution is simply that x is greater than or equal to negative 4 or less than or equal to 5. Okay. So case analysis is just that, is either the fact when your quadratic is greater than or equal to 0, recognizing that both factors are positive or both factors are negative, and if the inequality is less than or equal to 0, then you've got a positive times negative or negative times positive. Okay, so it is always possible that there could be no solution, and so think about what that might actually look like. Well, it could it be that maybe we have a quadratic, and so this is easier for me to show you graphically. If I have a quadratic that is fully above the x-axis, or it could even be that the vertex is on the x-axis, and I'm asking you, hey, when, for what values of x is the quadratic less than 0? So meaning when is a quadratic below the x-axis? Well, never, so there would be then no solution for that particular case then. Okay, so let's take a look at the last class example number 3. So the very first thing that we want to do is to go ahead and factor 5 minus 4x minus 3x squared. And so in this particular case then, we've got 5 and 1 and negative, 3x. Squeeze that in, so minus 3x, and this is going to be plus 1x. So 5 plus x times 1 minus 3x. Double check my multiplication right there, of course, because that affects whether or not we've got the correct quadratic, and obviously the trickle down is with your test intervals as well. So that must be greater than or equal to 0. So In order for that to be greater than or equal to 0, we either have, and if it helps you to write down positive, positive, or else the fact that we could have negative, negative. So our case 1 then is just that, positive, positives, which means that 5 plus x is greater than or equal to 0. And at the same time, 1 minus 3x must also be greater than or equal to 0. Case 2 is that negative, negative, which means that 5 plus x must be less than or equal to 0. And at the same time, 1 minus 3x must also be less than or equal to 0, meaning they are both negative. Why is it or equal to 0 is just going back to the original inequality itself. It also includes 0, so that's fine. So when we go through and isolate, then we've got then x is greater than or equal to negative 5, and in this case we can move around. We'll subtract 1, so negative 3x is greater than or equal to negative 1. And now remember, when we're dividing by negative 3, we have to flip the inequality symbol, so x is less than or equal to positive 1/3 then. So can we think of values that are greater than or equal to negative 5 and less than or equal to 1/3? Yep. Absolutely. So we can write that out as a single expression. You can leave them as two separate ones as well. That's totally fine. So greater than or equal to negative 5, less than or equal to 1/3. So that works, which should suggest that the other one wouldn't, but I think it's really important to still go through the steps just to make sure that we didn't make a mistake in case 1. So x is less than or equal to negative 5, and at the same time, again, subtract 1, so negative 3x is less than or equal to negative 1, dividing both sides by a negative 3, which means we're flipping the sign, so x is greater than or equal to 1/3. And is there any values that we can think of that are less than or equal to negative 5, but also at the same time greater than or equal to 1/3? And of course, can't think of a single value that satisfies that. There's no solution on this side, so case 2 does not work, which means that our solution is simply from case 1 there. Okay, great. Thank you for listening in, and let me know if you have questions.